All right, so this one looks scary, but if you just write it, it's okay. So, solution. Being self-adjoint means star is itself, right? And then we want to prove that ST,
The whole thing star.
yeah, star is equal to ST if and only if ST is equal to TS. Right? But this is almost given. So you can say that, well, let's prove this way first, okay? So suppose ST star is ST. Well, since ST star, we proved during the lecture that this is T star S star, right? If you forgot this, you can kind of remember that if you have A, B transpose, that's same as B transpose, A transpose, right? Conjugates don't do change of ordering, so conjugates don't do anything. So if you remember this, this is kind of obvious. And therefore, let me see, this is given for either case, right? So they're self-adjoint, so this is going to be TS. So having ST star equals ST implies ST equals to TS. And then the other direction is ST star is equal to T star S star equals to TS, but because this is an assumption that's equal to ST. Done. So. Okay, so this is a variation of an example problem from the book. So you're given some non-zero vectors, and you're given these two equations, but if you inspect these equations carefully, you see that this means U is an eigenvector for T with eigenvalue 2, and V is an eigenvector for T with eigenvalue -1. And we also remember that for normal operators, eigenvectors with two distinct eigenvalues are orthogonal. Yeah, orthogonal. Normal. That's where that name comes from. Okay. So what we know is that since T is normal, UV is 0. Okay. Now automatically, if UV is 0, then VU is 0 as well. Because these are complex conjugates of each other, and complex conjugate of 0 is 0. Okay, so we get these two for free just because of the normality and one of the theorems that we covered for normal. So it's now very easy because now you have U plus V. To calculate this, you first take the square, which by definition is same as U plus V and U plus V. So that's, if you have an inner product, you can always define the norm, and the norm is defined this way, right? So that's the definition. But then using linearity of the first component and also conjugate linearity of the second, you can basically FOIL this. Okay, so you get UU plus UV plus VU plus VV. Where these are 0 because of our things, but that's equal to norm of U squared, norm of V squared, which are 3 squared plus 3 squared, which is 18. Therefore, norm of U plus V will be square root of 18. Okay. Right. So this is fine for me. If you are somebody who likes to simplify, this would be same as 3 square root of 2, because 9 times 2 is 18, 9 comes out as 3. Okay, but then what about tu plus uv, t of u plus v? Well, same idea here. It's going to be, this is tu plus tv because t is linear, right? And because tu is 2u and tv is negative v, this is going to be norm of 2u minus v, norm squared, which is 2u minus v, 2u minus v. Again, you just FOIL this out, you get 2u plus 2u negative v plus negative v 2u plus negative v, and then 2 comes out as 2. Conjugate of 2 is 2, so you end up with 4 times uu. 2 comes out, negative 1 comes out, so it's negative 2 uv, which again is 0 because of this condition, minus 2 vu, again 0. And then negative comes out, so it's vv. And that's going to be 4u norm squared plus norm of v squared. That's going to be 36 plus 9 is 45. So that tu plus v norm squared is going to be square root of, sorry, without the square, it would be square root of 45, which is 3 radical.